We are delighted to announce that Salas has achieved remarkable success in the industry this year. They have climbed the ranks to rank 11th on Consulting Specifying Engineers 2023 MEP Giants and rank 8th on Building Design Plus Construction Giants 400 2023 Top Engineering and Architecture Firms list. Furthermore, they're celebrating their 11th consecutive year on the Inc. 5000 list. These achievements are a testament of their team's unwavering dedication and delivering top quality solution to their clients and partners. We thank Moisture Intrusion Solution, a Salas company, for sponsoring this particular session. With that, good afternoon, everyone. I'm Sim from Energy Management Association, and I'm excited to welcome you to another EMA webinar titled New Energy Codes and Whole Building Airtightness Testing. The speaker for today's webinar is Mr. Shanks. Stephen is a seasoned building scientist and commissioning provider with 40 plus years of experience and holds the role of VP for Building Enclosure Commissioning at Moisture Intrusion Solution, a Salas company. Merging physics and construction expertise, he adeptly bridges theory and practice. His proficiencies encompass building enclosure commissioning, air barriers, and whole building airtightness testing. Before we dive in, here are a few housekeeping notes. Presenters will be holding the question until the end of the presentation, but we encourage you to submit them at any time using the Q&A button. If you happen to be experiencing technical problems during the webinar, please use the chat function to inform the panelists, and our technical expert will assist you. This presentation is being recorded and will be available for viewing in 1 week. In terms of continuing education credit, everyone in attendance for the full webinar will receive a certificate of attendance sent to their email within 24 hours. And with that, I'm going to hand it off to Stephen to take over and start the session.
Thank you, Sam, and good afternoon, everybody. Again, my name is Steve Shanks. I'm with Moisture Intrusion Solutions, which is part of Salas O'Brien. So we're going to be talking today about energy codes and what those requirements are, and particularly around whole building airtightness testing, which some of us have been doing since the mid-2000s on federal projects, but it's relatively new on the commercial side, and trying to demystify that and reduce any concern or anxiety that folks may have regarding that. Again, as Sim mentioned, it qualifies for AIA, HSW learning units, also PDHs or USGBC. So what we're going to be talking about, particularly in the control layers for the building enclosure, is the impact of air barriers. We're seeing, depending on the part of the country that you're in, energy improvements between 10 and 40%. Also has an impact on moisture management, acoustics, odors, brings a lot of different benefits to it, both in new construction and retrofits, which, as many of us know, the value of building permits for existing building renovation rehab is now exceeding new construction. So we know that it's impactful, in some instances more impactful on existing building rehabs than it is in new construction, but still delivering great value. So learning objectives, we're going to talk about the codes, going to talk about functional performance testing for the building enclosure, and building enclosure, building envelope are similar terms. In my practice, we use enclosure. We're also going to talk about whole building air tightness test prep, the procedures, and then going to run through some case studies, some successes that folks have had just recently on the commercial side doing things that they hadn't done before. So this is one of my favorite quotes, and I'll usually drop it in. It's from Thomas Edison, who founded his company, the Electric Illuminating Company, in 1896, which later became General Electric. Object of all work, whether you're producing something or providing a service, is you have to think about it, be systematic about it, have a plan for it, be smart about it, be fair and honest in what you're doing, and then work hard at it. Sounds like most of my days. So I just always like to drop that in. So International Energy Conservation Code, the one that's the current model code that's out is 2022 or 2021, and it also references and incorporates ASHRAE 90.1 2019. So whole building air tightness testing in the Energy Conservation Code is required, also required in 90.119. So ASTM tests actually for large buildings now, E779, I'll talk about this some more, is more of a legacy standard at this point. It's been replaced and the code's been updated to reflect ASTM 3158. Also in the codes we have, there's a maximum allowable air leakage. And then there's also this grace range, which means if it exceeds a 0.4, but is less than or equal to a 0.6, then if you have identified your air leakage pathways, then you only need to repair those and provide proof of it, rather than have to go through the entire test again. And talk more about what that means in a little bit. Another part that's required in these new codes is, and it's something we've been doing on the federal side, like I said, for the last 15 years, is you have to have air barrier specific drawings. And these drawings, one is just defining what the meets and bounds for the air barriers are, which would be your conditioned space, not semi-heated or unconditioned space, but conditioned space. And in addition to that, you have to provide project-specific details. Some of these get a little tricky, especially if using different manufacturers on a project. So need to insist on letters of compatibility, which can be difficult to get, in which case the firm should be able to do that compatibility testing. And if anybody would like a presentation on this detailing and construction techniques for this, happy to revisit that at another time. So let's talk about code progress. And this was updated the end of June of this year. And it's already out of date. Adoptions, Louisiana has now adopted 90.119 in the Energy Conservation Code, and this is on the commercial side. That's what we're talking about in this presentation is commercial. I'm not going to talk about residential. That's a whole nother conversation. But Louisiana's adopted it. It's been adopted throughout New England. Chicago has adopted it. Minnesota is adopting it first of the year. Denver and Boulder have adopted it throughout the West and the Northwest. The state of Texas is currently in the process of adopting for all projects that have state money involved. You'll also notice looking at this that there are 8 states that have no statewide energy codes. There are 2 states that have no codes at all. That's Alaska and Mississippi. The others, Colorado, Kansas, Missouri, North and South Dakota, and Wyoming, have what's called home rule, which means there's no statewide code, but local jurisdictions are free to adopt their own energy codes. Also interesting is Chicago has this, Massachusetts has what's called stretch codes, where they have a basic model code, but then they have three stretch codes. So in Massachusetts, with their new energy code that's been adopted, there are now four different energy compliance pathways, depending on where they are in the state and the Commonwealth that they can pick up. So this is something that I think is significant, regardless of why you think or don't think that climate change or global warming is occurring. We have factual data, and we see just between 2018 and 2021, what do we see? We see warming towards the capturing all of Oklahoma, uh, cooling rather, that's capturing northern Oklahoma, cooling and warming that's expanding into northwest Colorado. While at the same time, we have cooling moving down here. In the mid-Atlantic, I'm in Richmond, Virginia. It's particularly impactful. You see, North Georgia is now all climate zone 3, no more climate zone 4. See what's happening in Tennessee. North Carolina was pretty evenly split between climate zones 3 and 4. Now, with the exception of the mountains in the western North Carolina, it's all climate zone 3. And Virginia, which had been predominantly climate zone 4, now it's climate zone 3 creeping in, and it's effectively one county away from where I live. So in the next climate zone data that we'll get at some point next year, I expect that I'll be moving where I live from smack in the middle of climate zone 4 to being picked up in climate zone 3. So warming's definitely happening up mid-Atlantic. You also see the warming that's occurring in up towards the New England states. So regardless of what you think, it's having a very measurable impact in changing our codes. So building enclosure cost studies. So Dr. Evan Mills at Lawrence Berkeley started doing enclosure-related cost studies back in 2009. And over his several studies, he determined that enclosure-related improvements is the single most cost-effective strategy for reducing energy costs and greenhouse gas emissions in buildings today, which would also go towards decarbonization. And what he found I thought was interesting, that for existing buildings, looking at nationwide, about a 16% improvement in energy, new construction, 13%. And I think that may be because in existing buildings, we're going to know what those air leakage pathways are before we start construction. So I think we're more effective in addressing those during the course of renovation and rehab. So here's some more cost, and I'm going to go through some other cost studies as well. Estimated improvements in commercial energy code. This is from Pacific Northwest National Labs. And most states that have energy codes, many are still functioning on 2007. But you'll see from 2007 to the 2019 and 90.1, we have about a 40% improvement in the performance of the energy code. So a lot of money to be saved there, good investment. So we had a big jump and we keep improving. ASHRAE, which puts out the 90.1 and has already published 2022. They actually have a goal by 2031 that their codes will effectively, when all the different pieces are adopted and utilized, provide net zero construction. So that's the movement that's been picked up in codes over the last 20 years. And that's what we're going to continue to move towards. And also, I think it's important to note that the adoption of the International Energy Conservation Code in 90.1, the adoption of those by jurisdictions has funding support in the infrastructure Reduction Act that Congress passed. So that's why I think jurisdictions like Louisiana were moving towards it, not only because it'll save the people of the Louisiana a lot of money, but the cost of rolling that out is being picked up within the IRA. So here's another study. This is from 2012 through one of the DOE programs. And they did air sealing retrofit of a 244 unit low rise multifamily in Durham, North Carolina. So we're in climate zone 3-4. Did a comprehensive program, did testing pre and post retrofit, effectively reducing total air leakage by half with the retrofit. The cost of this, and I think part of this is because of the scale, and they address this in the report, and I've got the link in the bottom of this, it was such a large project. So 14 cents a square foot, and with modeled energy savings of 10 to 19%. So controlling heat loss or gain through the envelope to save energy, improving comfort by eliminating drafts and temperature swings, avoiding moisture problems that will typically form from uncontrolled air leaks, minimize air movement between apartments and crawl spaces, so that improves the environmental quality, and also equipment performance. It doesn't have to work as hard to heat and cool. So this comes from Department of Energy. This was data presented at a March 2017 meeting, and you'll see so climate zone 4. So let's read climate zone 2A first. So this is Austin, Texas. This is Louisiana at ceiling rate. So zero point 0.4 is their code. But I'll tell you that almost all the projects that I've been involved with in these jurisdictions are getting a 0.25 or better, and that third to a half are actually doing at or better than a 0.15. And that's a CFM per square foot per minute air leakage at 75 Pascal or 0.3 of an inch water gauge. So assuming that you're moving at a 0.25, looking at 5% energy savings in Austin or Baton Rouge, in Raleigh would be looking at close to 10%, in Richmond, close to 20%, in Boston, also 20%. But as I said, these buildings are doing better, so it's pushing closer to an effective 30% savings. Oak Ridge did a program with NIST and with also the U.S.-China Clean Energy Research Center to develop the air leakage calculator, which is titled Energy Savings Moisture Transfer Calculator. And the link is shown here. So it's a little funny. The baseline of this was a leakage rate of a little over 1 cubic feet per minute leakage at that 75 Pascal, which we would call CFM 75. So the blue is a 0.4 leakage rate. So looking at where I am, that'd be about they're projecting 48% energy savings. The orange would be a 0.25. And then the red is a 0.06, which would be a little better than a passive house. So all these studies together, in case anybody ever asks you if there's any kind of cost impact, what we typically see is a return on investment of about 1.2 years. And you can see there's some pretty significant energy savings that are coming back pretty quickly to the occupants, owners of these buildings. So this is my other favorite quote. It's from Wernher von Braun, the father of modern rocketry, who said, "One good test is worth 1,000 expert opinions." Seen this frequently misquoted as one test, and that's not true. I'm sure everybody on this call understands that Just a test isn't always having value, but if it's a good test, then it can deliver tremendous value to a project. So these are tests that many are probably familiar with on water penetration resistance. Here's an ASTM E1105 on an AMA 503. This is a curtain wall section. Here's some sloped glazing. Here's the spray rack working on the surface. Here's the nozzle test, which is used for subassemblies and assemblies. And then the 501.1, which is the aircraft engine, and which is typically what we end up having to use on curtain wall because it's in large curtain wall sections, it's just not practical or possible to divide out to be able to do a separate chamber test unless you have a smaller area like this. Also, air infiltration testing. You'll see up here, that's what's called a tear sheet on the outside, where we pressurize the inside with the tear sheet in place to figure out what that baseline air leakage is around just the chamber itself. Then we remove that, and the difference is the actual air leakage through the assembly. These are all 1186 tests, which is air leakage pathways. Bubble gun is around fasteners. Here's an example of air leakage and a fenestration. I like to use theatrical fog or smoke because it's a much visually easier way to see how air is moving through a building. And then the blower door testing, which we're getting ready to talk some more about. So there are, within ASTM and the building codes, 3 whole building airtightness test methods. I mentioned E779, which is a legacy for most commercial. It's more applicable to residential, so it'll continue there, but for large building, for commercial, we consider that a legacy standard at this point. E3158 is the standard test method for a large or multi-zone building doing whole building. For apartment units, for individual units in a building, that'd be E1827. And these are typically at a sample rate of 1/7 or 1/8. It's an unguarded, meaning that each individual unit has to be fully sealed on all 6 sides, top, bottom walls of each apartment, and tested that way. Also, I mentioned the grace range, which means you have to have thermal or smoke that's been performed so that you know what those air leakage pathways are. So the code will specify that this test be done, that these tests be done, but it does not specify that thermal infrared. And it adds a negligible cost to the test, and it gives you 2 things. First of all, if you need it, it provides you air leakage pathway information for grace range, and regardless, it gives you good lesson learned information so that designers and contractors will know how to better detail and construct the next building that they're on. I think it's important to note that until very, very recently, there was no certification program for people who do this test. The Air Barrier Association initiated training earlier this year, and they are just, I think, as of last month, rolling out a certification program. Regardless, and this is something that we developed for Corps of Engineers and included in their spec, is a pre-qualification for the test agency that you're going to use. So I'm on both sides of the table, and I see a lot of reports that were generated for projects that just say they didn't deliver the value that was anticipated. So this is a way through a pre-qualification to make sure that the firm and person that you have working on your project actually is able to deliver what the owner intends. So for whole building airtightness testing, so NIST back in 2005 measured 203 commercial and institutional buildings had an average air leakage of 1.55 CFM per square foot at 75 Pascal. Some of the other baseline for energy improvement, we're using at or near a 1 CFM per square foot, which I think kind of fell short from what we knew from actual performance. So I think those energy savings from what would be a normal commercial or institutional building, I think the energy savings are a lot more. So in terms of range of energy standard, there's 0.4, which is IBC, Massachusetts Model Code GSA, the 0.25 CFM per square foot for the Corps of Engineers for the Green Building Code, 0.1 CFM per square foot, that's state of Utah for their state buildings, Massachusetts, New York City Energy Code, many institutions. I'll say there's a middle school in Charlottesville, Virginia, about an hour outside of Richmond, which actually in this new construction referenced the New York City Energy Code and are requiring a 0.1 CFM per square foot. So owners know that it's going to be cheaper to own and cheaper to operate with this code that we've got plenty of data showing that contractors, designers and contractors can get there with not a whole lot of extra effort from what they're already doing. Then there's 0.08, which is this is passive house or FIAS. And it was interesting, did a presentation with the largest contractor in New England. And they said that all of their multifamily that they have on their books as backlog are now using FIAS because they know that it's better occupant comfort, it's cheaper to own, cheaper to operate, and will extend the life of the structure. So let's talk about whole building. So this is what a test result will look like. Multi-point regression gives us the statistical information so that we can confirm that the test results are valid. And it also lets us know how the building's performing at lower air pressure. But this is mainly for repeatability and validity of the data. So test prep. So planning, of course, is important for anything. Have to have a test plan, have to have meetings with the right people, then make sure that the people that are engaged in the project know what their responsibilities are, because that's not something that's going to land in the specs. So who's involved, who has a role, who has contributions to this process? Not only testing agency, architect, GC, owner, your commissioning authority, that could be MEP, and or your enclosure commissioning, trade subcontractors, HVAC, electrician, controls, plumbing, and then what the timing and scheduling for this testing is going to be. So the process itself will be pre-test, prep of the building, the testing, demob, and reporting, and I'll talk about some of that timing on site for the testing in a little bit. Testing agency responsibilities, along with diagnostic, air leakage, site detection, which I think is important to include in every project, and then reporting. So this is something that people still struggle with on this test, and that's thinking in terms of the 6 sides of the building that form the air barrier, the 6-side surface area for the test. So it's normal and customary that the designer of record provide, and then the testing agency and GC confirm the official test boundary for the 6-sided building enclosure. So I think this is a great diagram to demystify just what gets included in all the different aspects of calculating that, from overhead planes to plaza decks to alcove planes, including floor slab. It's essential to know whether or not your building enclosure meets, and whenever it's wrong, it can be the difference between a pass or a fail between a building that's performing the way it's supposed to and a building that's not. So I mentioned before, air test boundary is the conditioned space. It's not ventilated, unconditioned, or semi-heated areas, which would be ancillary areas. It's the conditioned space of the building that is the subject of the test. So there are GC trade responsibilities. There's essentially two types of tests. There's architectural only, which measures the work that the contractor did, and you essentially mask out all the mechanical. And then there's architectural plus HVAC, which evaluates not only the air barrier as constructed, but the mechanical units and how they're going to perform whenever the building's in use. The ASTM E3158 has got a comprehensive building prep for each of these test boundaries. And that's why it's important in that pre-test meeting that each of the trades are there along with the GC so that we can talk about this and talk about what's different and what's the same between them. Part of that is identifying where fans are going to be set up, and how the pressure taps to identify interior and exterior pressures are being done. Now, I'll make a note here that there are two common mistakes that I see in reports. One is that E3158 requires that you have these interior-exterior pressure taps on various elevations of the building to represent the range of conditions present on the day of test. Some test reports have one manifolded test value for that, but that's incorrect. You have to have individual interior exterior pressures at different enclosure elevations. Also, there's a requirement that there be no more than a 10% pressure difference between the two furthest points in the building, which means you have to be capturing those induced pressures. It's not uncommon to see that missing from a report. So that's just an FYI to make sure that you're going to get that from your provider. So what does prep look like? So it's going to be masking of exhaust fans. It's going to be masking of louvers. It's going to be masking. So at louvers, the other side of the RTU will typically mask too, because we're pressurizing in both negative and positive directions. So I want to be able to resist that 75 Pascal, which is equivalent to about a 23, 24 mile an hour wind. When people ask me how long the test is going to take, that is always a function of the quality of the building prep that was done by the GC and trades. And we'll walk over and we'll verify that before we do the test. But the masking off of the interior of the RTUs or HUs doesn't always happen, and it's almost always a problem. Just like inadequate taping and sealing for louvers is frequently a problem. So in terms of the setup itself, understanding the door sizes, understanding the limitations of equipment. You see here where the actual door opening was taller than the frames that were being used for the test. So I had to put a blank in there, and then knowing from previous experience, had to brace that. Also, there's a lot of plumbing and wiring that goes into setting up. The bigger the test, the more of this that has to happen. And even though for most buildings, you can do that in the morning, test in the afternoon and evening, though for a large building, it could be a setup that starts the day before. So we're also frequently seeing multi-zone testing in a high-rise. That could be, say it's a 23-story high-rise and you want to start build out on the bottom 10 or 12 floors. So you'll compartmentalize those so that you can test those in their entirety and release those for build out while the contractor's finishing the floors above. In this example, this is a precast building here. This is a pre-engineered metal building here. And yes, we test pre-engineered metal buildings all the time with a 0.25 maximum allowable. It's just a matter of proper detailing and proper coiling doors. It's not that hard to do. So what you have to do here is create this pressure equalized wall, which you're essentially constructing an air barrier that separates these two. When actually we did this test, this was a bust, and we ended up testing this as an entirety, which the owner accepted, but it did not meet what the intent was in the initial design. So hopefully you don't get to a point where you're having those difficult conversations. So let's talk about diagnostics. So ASTM E1186 is the standard practice for air leakage detection, and it has additional reference standards. There's an ISO standard, which is very comprehensive. It's great reading for thermal infrared. There's C1060, which identifies missing insulation and envelope cavities, and many will be familiar with C1153. That's the standard for identifying wet insulation in roofing systems. So thermal infrared, you have to make sure you've got somebody that is properly certified. They have to be a minimum NDT level 2, and they have to be supervised by an NDT level 3 who's also validating procedures. So there's a lot of folks running around out there who don't have minimum levels of qualification and don't know how to differentiate between a relevant and non-relevant indication. So, and this is all part of what's picked up in the pre-qualification test. I mentioned smoke and theatrical fog. A great way to look side. There's also tracer gas, which is more typically used for safe rooms in industrial settings. Oak Ridge is doing work right now to develop a technique that we can use on commercial buildings, because the benefit is not only see the leak, but you see how big or small the leak is. Right now, we can typically only identify the largest leaks, then we plug those, and then we have to keep working our way down, like fingers over the end of a water hose. So that's something to look forward to, but that could be 5 or 10 years out. So I've got 3 case studies. This is one. You see, this has got a mechanically fastened wall membrane. The performance was terrible. It's 0.724. So I had leaks around these service doors. Had leaks. You see these pipes going through? Yeah, not sealed around those. So that's just all cool air moving across. Here's a hole that they left in a wall. Here's a non-gasketed sprinkler fitting. So these are all the kind of details that get picked up in the design review that should be part of any project where this is a requirement. So 2 large building case studies. One is Texas Department of Transportation did a campus consolidation. All the way, they have a central state warehouse, central state laboratory, and a central state office building. The laboratory and warehouse did great, all met below what would be a FIAS level. The energy savings are going to be tremendous. So the office building, you see, it's got a lot of curtain wall, had fluid applied, and peel and stick air barrier, also metal stone, stone masonry, low slope, single ply, over 350,000 square foot of enclosure. Marvin Mock was architect, and Vaughn Construction was the GC with about a $300 million construction value. So in these tests, so ceiling tiles, suspended ceiling tiles, and if you have a UFAD, computer floors, they're removed at a rate of about 1 per 500, and also minimum 1 per room, because we have to connect all the building. Remember, there can be no difference between greater than 10% between the 2 furthest or most remote points in a building. And you see the louvers, you see exhaust fans. Here's the interior. There's the ceiling blower door fans being set up. So this is one where originally it was going to be divided into two zones, a zone A and B and a zone C. So what had changed from the original bid documents that we've been given to prepare these from the as constructed conditions, that they had a huge pass through on each one of these floors. So that means we had to do a bit of scrambling, but we already had sufficient fans on site. So we could pressurize this entire building, and it came out at a 0.121 CFM 75. So this is the first large building that this GC had done. That leakage rate was 43,000 CFM. What that means from a maximum allowable 144,000 is that for every minute that that building was operating, there was 100,000 cubic feet every minute of conditioned air that was not being pushed through the envelope. 100,000 cubic feet per minute of conditioned air not being pushed through the envelope. So you don't even have to have complex energy modeling to know that there's tremendous savings available from that. So here's the other one. This is Amazon headquarters in Arlington, Virginia. This is what they call METs 7 and 8. These are two high rises, 23 up, 4 down. Curtain wall, storefront, terracotta, metal panel, 2.1 million square feet of floor space. See the building closure areas. That north building's a little smaller. It's 500,000 as opposed to almost 600,000 square feet of surface area. Big test, 41 fans for the north building, 48 for the south. The architect was ZGF, which has done a lot of work on the West Coast, but this was a new requirement for the DC office. And Clark Construction, big sophisticated contractor, has done a lot of this on the federal side, but their commercial group, this was, from what I understood, to be their first large building on the commercial side. So I mentioned before about conditioned space and ancillary space. So you see separation here. So these are some retail areas that they have that are being tested separately. So this area right here at first floor are entrance spaces that are semi-conditioned, that are not a part of the main conditioned space. So this was something that we spent a lot of time on, going back and forth at the first level for the north building, south building. South building also had a central utility plant and kitchen, which were not included, and that ceiling done properly, along with what was happening up on their penthouse levels. So you can see a lot of planning goes into it. So we worked about 6 months, beginning in casual conversations with the senior PM and their senior enclosure superintendent, along with their senior QC folks, talking about what the process was going to be. Had drawings on each floor showing what the sequence was going to be. So just so you know, on this is about as big a building as many of us will do. And even if it's a taller high rise, it's likely going to be compartmentalized. So you're never doing over about 20, 25 stories at a time. So we showed up on a Thursday afternoon. We got unrestricted access then to begin setup. I mentioned a lot of cabling, a lot of tubing to run. And testing, after we finished the setup Friday morning, we started testing Friday afternoon, continued into Friday evening, and completed the testing then. And then demobilized everything before noon on Saturday. Probably had, I don't know, 18 people that were out there helping from the testing agency, and then a handful of carpenters and a couple from each of the trades along with the GC's reps. So you see how it did. I mean, it did great. On the south building, was 37% of what the allowable spec had been. The north building was less than a quarter. So again, with a requirement of a 0.4, that means that they're pushing out 150,000 cubic feet per minute of conditioned air that is not being pushed out through the envelope. Around 150,000 cubic feet per minute of conditioned air that's not being pushed from the inside to the outside. So money in your pocket, better comfort, better resiliency, cheaper to own, cheaper to operate. So obviously, good process in all this is going to end up with a happy ending, which is what we all want. Takeaways. So if you're not doing it today, you're going to be doing it shortly. It's very impactful. It's an easy, convincing sell to any owner who's going to own a building based on ROI beyond about 1.2 years. Certainly compelling for an institutional owner. So it depends on design, process, detailing. Make sure you're using materials that are tested and evaluated. You have knowledgeable and certified installers, along with quality assurance observations, testing by experienced certified building closure professionals. So that's the end of this presentation. This is my contact information. So now going to open this up for any questions that anybody might have.
Perfect. Thank you so much, Stephen. That was an interesting session for sure. Now we are open for the questions to come in. So please use the Q&A button to push in your questions that you might have, and Stephen will be addressing them now. To start off with, I do see 2 to 3 questions in, and the first question would be, at what stage of construction shall the blower test be performed?
So that's a good question. And it has to be performed. The final test for acceptance would be when commissioning is substantially complete, meaning controls are at or substantially complete, means that everything's being conditioned. You're probably to the point where you're getting ready to move furniture in. For these large buildings, I always recommend that we select areas of the building that have some of the more challenging details and go in and create even a temporary compartmentalization so we can test those and see where air leakage is occurring so that can pick up any touch up or adjust in the technique. So I would say at the initial phases of construction, it's recommended. And then the final test is always required right at the end of construction, about the time you're bringing furniture in, and usually not many weeks before your CO.
Perfect. And the next question is, for projects that are testing to the local energy code, assume 2021 IECC, is the test carried out according to the building envelope preparation method, excluding the HVAC openings?
Right, so that is going to be, so if you have a building closure commissioning process, this is part of what's discussed at the point of establishing the owner performance requirements and also basis of design. So to meet the code, the code is the worst building you can construct. To meet the code minimum, I would interpret it to say it would be that architectural only with HVAC openings excluded. But the code also has requirements now for maximum air leakage for fenestrations, for mechanical units, for overhead and coiling doors. So I think I think that it's going to be, and my recommendation is always to, at OPR, establish that the HVAC openings will be included. so that that becomes an explicit part of the basis of design going forward. But that's when that conversation needs to happen and that decision made. If that doesn't happen then I think it's likely going to be an architectural only test, which is, the fair test for the contractor. But like I said before, if you want to know how the building's actually going to be functioning whenever it's in service, need to do that architectural plus HVAC as well.
Interesting. Perfect. The next question is, how can we make sure that the area under test is isolated completely?
So we do that under test. So first thing that we'll typically do before we run all that multi-point regression and everything is we'll pressurize the building to see if it's going to be a failing or passing test. We get that pretty quickly. And if it looks like it's going to be failing or close, then we'll go ahead and do some diagnostic testing at that point to see if it's going to be a fault in the as constructed condition or in the masking condition. So, but that's also a benefit of doing the earlier phased testing in areas where expect that you may or may not have a problem, just to verify that.
Perfect. The next question is, how does this relate to the amount of unconditioned infiltration that is entering a building?
So I work under the assumption, so I'm not only a building enclosure commissioning provider, but beginning in the late 90s, I started doing MEP commissioning. That's the commissioning that I did first. And then because my training was architectural engineering, got more active in building enclosure commissioning beginning early 2000s. All that to say that buildings are presumed to be under positive pressurization. It's not uncommon in the South where you'll have a winterizer that'll kick on that can move a building to negative. So whatever the amount of infiltration is from interior to exterior won't be the same, but it'll be similar to exterior to interior, which is why I think a commissioning process for MEP is every bit as important as it is for building closures, because you want to make sure that you're managing those set points through all the different seasons, and that's part of what happens in a routine commissioning process.
Wonderful. The next question is, any guidance on budgeting for fees?
So that's going to depend on obviously the size of the building and the number of fans it's going to take and what it's going to take to mobilize and prep. So for a large building like Amazon, that fee was, and you saw all the time that took to get ready for it, and I mentioned number of personnel and equipment. That total fee was around $100K for both of those, and I think the contractor said that their cost was around 30. That being said, a typical building, which is going to be, don't anybody quote me on this. This is about as wild an assumption as there is. But for a building, say 4 to 6 fans, maybe $12,000 to $15,000. 6 to 9 fans, maybe around $20,000. If it's a lot less than that, then I'd be all the more concerned about whether or not the agency is qualified and doing all the things that they have to do to make sure that your equipment's calibrated, that their people have been trained and certified.
Perfect. Thank you. The next question is, the test is conducted at 75 PA. What pressure does the building normally operate at?
So the test is conducted at 75 Pascal, which is 3/10 of an inch water gauge. Most buildings are positively pressurized at a 0.03 to probably it's range 0.02 to 0.04. inches of water column. So with the test conducted at 75 Pascal, 23, 24 mile an hour wind, so that number was picked for a lot of different reasons, including what were some wind zone calculations done at the time. And then you also have to have a standard basis for a test. So this is going to be more than a building's normally going to be operated at. But I mean, I'm sitting in a place where we had a tropical storm blow through last weekend, and we had envelope loads that were at least at 75 Pascal. So we want to make sure that the building's going to function at those loads as well. If you're out in the Midwest, you're going to have those straight line winds coming through. So yeah, it's for a lot of different reasons. So there's what the building normally operates at, and then what the building has to perform at during its life cycle.
Perfect. Next question is, can you elaborate on the projected energy savings mentioned? Was this based on model building information, that is ACH data or similar? What do you usually do to provide a projected cost saving rank to a potential client, that is reduced HVAC energy consumption?
So that's always going to be an estimate, even though the energy models are getting better, and NIST actually improved the model further with a study they did last year, that waiting for that to get incorporated into the calculator. So I would refer, so I gave you four different model and actual cost saving data sets in the presentation. So I would, if an owner asks that question, then that's where I would start. And you know, a lot of times I'll have some specific data from other clients that I can refer to within the geographic area to give them some better ideas. But I mean, if you're an institutional owner and I can save you a minimum of 5% over the life of your building just by adding this air barrier, that's a lot of money. But if you're in the Mid-Atlantic and it's 15 to 20%, that's a really lot of money. So modeling gets you close. The real life is what's important. That's why we always encourage monitoring based ongoing commissioning, so that the mechanical is functioning the way it's supposed to, and we're able to track that related envelope performance at the same time.
Perfect. Thank you, Stephen. The next question is, how do you test tenant areas where there is no HVAC ducting, only main air supply duct?
So those tenant areas are going to have their own separate HVAC systems. So, and each tenant is going to have their own thermostatically controlled. So I don't know, you know, it could be set up by zones. There's a lot of different ways to do that. But each one of those individual tenant build outs, each one of those spaces will be compartmentalized and separated and have their own separate test. So, yeah, I would look at whatever the individual design is, and that's something that needs to be considered in the basis of design. You know, it would have been addressed in the OPR, then considered in the basis of design, and be subject to the design review process. And we'd verify that during the course of construction.
Perfect. Thank you. And the last one that I see here is, what formula would be best to utilize in computing OA loading to better size makeup air to provide adequate air for a slight positive pressure in a lab? Of course, dB or WB or RH dew point parameters have to determine BTUH.
I can tell energy managers are in this presentation. So that is outside of the scope of this. I'm sure that there are many other people in this presentation who would have an answer for that. And I actually have several different ways to get to that out of the ASHRAE Fundamentals Handbook. So, but yeah, that's a separate conversation. Important question, but separate conversation. Sorry, William.
Perfect. If you have time, Stephen, can we go ahead with one more question?
Sure.
Perfect. So one of the Kickstart question was interesting, and that would be, why do you think that the climate change is occurring? I was waiting for
So,
this one.
yeah. So, I actually addressed that a bit in the presentation. And of course, there's a diversity of views, and a lot of that's become politicized. And what I always refer back to is the science. Whatever the cause is, or whatever an individual thinks it is, we have climate data that shows that climate zones and design, the basis of design is changing. And in some areas, dramatically, just over a 3-year cycle. So, yeah, that's a conversation that I don't engage in unless I've had several beers and it's somebody who's a good friend and wants to just arm wrestle over it. But yeah, the answer is it doesn't matter. Something's happening, and we know what it is, and we know what we have to do.
Perfect. Thank you so much. And I would just request you to move on to the next slide.
Absolutely. Oop.
No worries. Let me go ahead and quickly do that. I have that right here.
Yeah. Out there, we can already stop the screen sharing.
I can grab it. Thank you so much. But again, thank you so much, Stephen, for such an insightful Q&A session. While everybody's still here, I just want to go ahead and invite each one of you for the virtual O&M training and for engineers and facility managers. That is going to happen on October 18th and 19th from 1 p.m. to 5 p.m. EST. This is basically just to make sure that you discover basically the front line of energy efficiency with our course tailored for ambitious building personnel. Our certified instructors will guide you through energy management essentials from build evaluation to code compliance and to enhance your facilities performance. Basically, to have more information on this thing, just go ahead and visit www.energymanagement.org. You get to earn a certificate of completion, 8 AIA LUs, and also to keep the handouts and recordings for future review as well. I just want to go ahead and thank each one of you to basically attending this session and Stephen for this session again. Thank you so much.
Thank you, everybody. Hope you have a great and safe day.